Very good morning to students. Today we are going to learn about the rock failure criteria. How the rock is failure in the way which is based on there is a different theories are available in the scientific methodologies that proven that the rock can be failure such a way that these things will be studying in this lecture. My name is Karuna Kumar, HOD Mining. Rock mechanics and strata control is today lecture. There is a failure criteria of rock. The failure criteria of the rocks is subtopic is also same. Well, this is the one view of the underground mine. Uh, failing factors generally stress, strain, energy. These three are very important for failure of rock is concerned. Um, particularly the stress principle or normal stresses are there. These two are very important for the failure rate calculation. The shear stress is also very important, and principal strain is also one of the factor, and energy, that is a maximum strain energy. Shear strain energy is also one of the categories of the failure factors. The failure criteria is also classified into maximum principal stress, maximum shear stress, maximum principal strain, and maximum strain energy density, maximum distortions energy densities. These are the categorized here. The figure is also showing the vertical force acting in P. The strain and stress relations also given here. Very example of the Hooke's principle is also given here. The failure criteria can be the simplified Hooke's formula as per the strain, stress versus n. There is a hook limit is there, from which limit plus some elasticity limit is there, then upper yield point, and then this is a failure. This cannot be restored again. That is called a sigma y, the failure up ultimate upper yield point. The every material have its own the Hooke's limit and also elastic limit as well as the upper yield point. So this is the very interesting of a failure criteria calculations purpose. It's useful. Stress versus strain curve is showing here. So that load is called the vertical stress sigma y. The vertical pressure is acting on that. That's the maximum pressure with withstanding the material. So generally, well-known practice relation between a component of stress and those strain have been established by the experimentation. These relation are known as Hooke's law, assuming the rectangular parallelepiped with its side parallel the coordinate axis acted upon by the normal stress sigma x uniformly distribution to two opposite sides. The magnitude of the normal strain epsilon x is given by the generally sigma y by these things. There is also Poisson ratio we can be calculated basic differential equations. Uh, it is a major items. So next, coming to the maximum principal stress theory is one of the generalized theory we are using. When the maximum principal stress induced in a material under complex load condition exceeds the maximum normal strength, a simple tension test, the material fails. Good for it is a bitter material. This is one of the theory for the maximum principal stress theory. The sigma 1 greater than or into sigma ultimate. Uh, this is one of the principal maximum principal stress theory. So then the criteria for failure is specified in the mechanical condition, uh, under which solid material fails by fracturing or by deforming beyond some specific limit. This specification may be in terms of the stresses, strain, rate of change of stress, rate of change of strain, or some combination of these quantities in the material, because of materials are tested under a mechanical condition equivalent to that which they will be express in service. It is necessary for engineering purpose to have valid criteria of failure. However, there is a definitely recording a criteria of failure that is valid for all classes of rocks and for a mechanical condition. Hence, before a criteria of failure is specified for use in treatment of rock structure problem, as the examination of the mechanical condition that normal exist in the rock in and around number one opening in the is in order. There is a base things. Maximum shear stress theory is also there. Another theory, when the maximum shear strength in an actual case exceed maximum allowable shear stress in a simple tension test in the material case, good for ductile material. This is the above is a good for brittle material. This is a good for the shear stress is giving the good result for the ductile material. So you can be chosen which theory is better for the which material based on these two. And maximum principle strain theory. This is also one of the better theory for the rock failure criteria find out. When the maximum normal strain is actual case is more than the maximum normal strain occur in a simple tension test case with the material, but is not recommended. Sigma y by e is the strain of the maximum. Here we are using the maximum simple the sigma y by 2 half of that one. This is sigma 1 is a more the ultimate more than that. Another theory is the maximum strain energy density theory is also you're using. The Mohr circle is also showing here. When the total strain energy in an actual case exceed the total strain energy in a simple tension test at the time of failure, the material fails. Good for a ductile materials. This is a when the total strain energy the actual case exceed the total strain energy in a simple tension test at the time of failure. The material falls. Good for the ductile material. The sigma y square by 2e. So maximum distortion energy density theory, when the shear strain energy in the actual case exceeds the shear strain energy in a simple tension test at the time of failure of the material falls, the highly it is a recommended sigma y square by 6j. This is a maximum restoration energy density theory. Comparison of the all the Rankin principles and when into copper, aluminum, case, iron, steel. These are the other comparison sigma y by sigma 2. These are the comparison to study for the different theories. So the brittle material for the failure criteria, the maximum principal stress, the maximum principal strain, maximum strain energy density. These two are using for the brittle material. And ductile material, maximum shear stress, maximum distortion, energy density for uh, uh, failure criteria for the ductile material. So this is a very interesting, the brittle material and ductile material. The concept of the failure, tensile failure, shear failure, failure criteria, more Coulomb failure criteria. So concept of the failures are basically tensile failure there, shear failure there, failure criteria, more Coulomb failure criteria also. We are using for concept of the failure, tensile failure, shear failures is concerned. So concept of the failures occurs to any solid material when the sufficient large stress is applied. The material does not return to its original state after the stress relief. Mode of failure depends on the stress state and type and geometry of the material. The fatigue makes failure to occur below the stress level. The failure occurs to any solid material when sufficient large stress is applied. The material does not return to its original state after the stress relief. Mode of failure depending on the stress state, depend type of geometry of the material. The fatigue make failure to occur below the stress level. So this is a uniaxial test for the particular stress is applied to the end face of the specimen. No radial confining stress, also called the unconfined comparison test using. So uniaxial test is the most popular test for the underneath the UTM. You will bring the cracks different the radial conforming stress. The is called unconfined compressive test is called UTM. Under UTM, the specimen to put into and apply to the load, the where the breakdown that load can be calculated. Because of the stress concentration existing the near the surface underground openings also similarity you have to apply the same things into the then here the elastic region is given specimen return to its original state after the stress relief. The permanent change behind this point, the specimen does not return to its original state after the removal of the stress. Uniaxial compressive strength, the peak stress, that ductal region, a permanent deformation, but can be still support load. Ability to withstand stress decreases rapidly as a deformation increases. So these are the very categorized uniaxial compressive strength. The yield versus this is a strain. This is ellipsis is showing that a strain in z axis, sigma x is a stress. This is the failure compression uniaxial compressive strength material failure. That is called ductile. This is the elastic nature up to here. The other part is where the start to down, that is called ductile, and remaining brittle, the remaining portion is brittle. So this clear characterization. So elastic region, that is a region from the here to where the start, the hooks limit. Specimen return to its original state after stress relief. So once you have to load released here, it will come to a normal position, so that there is no change in occur. So that is called elastic limit, Hooke's limit is called. So that region, up to that region. Next yield point. See here is the start yielding. That is showing here exactly here this position. Uniaxial compression stress region. The permanent change behind this point. So once the load is applied behind the, for example, 10 megapascal. So 11 10.01 box is on what is called the yielding point. So you can't come to the original position of that. So permanent change behind this point is spacepan. Spacepan does not return to its original state after removal of the stresses. So uniaxial compressive strength, the peak stress, that is called the ultimate stress, you can say. So that is a failure, highest the bearable, the material bearable load from the set. So ductal region, so the permanent deformation, but it can be still support load. The ductal region, the permanent deformation, this but can still support load. Next, brittle region, the ability to withstand stress decrease rapidly as the deformation increases. So this is a complete idea for the failures and it behavior of missions. You can note it down in the notes for better understanding of the further lectures. Triaxial test, in addition to axial stress, confining pressure of the different magnitudes is applied to the circumference of the cylinder by confining oil system. This is a triaxial test. So when you are applied only vertical, but in in situ, but mine is concerned. This is a stress concentration is in around that. So triaxial test is the best for that one. So that is showing here. Triaxial test is concerned. And two principal stresses are equal. That is a process. Axial and confining loads are increased simultaneously. Unit and prescribed hydrostatic stress level is reached. Confining pressure is kept constant while axial load increases until failure occur. So sigma Z minus sigma R, that is increasing confining pressure. Difference in principal stresses is plotted against the axial deformation. Specimen can still support load after the failure due to the high confining pressure. It is called work hardening or strain hardening. So these are the showing the similar epsilon z. So sigma z minus sigma r is there. So this is the increasing confining pressures. This is the increasing confining pressures. So it shows that different situation, different principal stresses are plotted against axial deformation. Specimen will still support load after failure due to the high confining pressures called the work hardening and starter. This condition, the above condition is what is a given triaxial load. This is conditions. So so that vertical horizontal forces are acting, so that the vertical pressure is more required. So because it's not allowing yield, so automatically the strength will be more. That is shown in this one. Well, next I am showing the uh, Carrara marble. It is a different marble. It is how the failure of the different loads in uniaxial compressive strength. So sigma 1 by sigma the megapascals. This is axial strain. It's a 23 point megapascal, 50 megapascal, 84.5 megapascal, 165 megapascals. So sigma 3 the 326 megapascals. So it is a vertical axis. In axial test is conducted here. So 0 megapascal. This is a one marble. It's abrupt brittle failures for particular X location. Tensile failure, when that pull up down and up, the tensile failure occur when the effective tensile stress across some plane is a simple exceeding the critical limit is called tensile stress. So how to know that this particular specimen strength then when a pull out so where this break that is called as a tensile strength of the particular material. So tensile failure is caused by the stress concentration at the edge of the thin crack oriented normal to the direction of the least compressive principal stress. For isotropic rocks, the conditions for failure will always be fulfilled first for the lowest principal stress. uh, for isotropic rocks conditions, that is isotropic conditions are there, anisotropic and isotropic conditions are there. The strength and elastic properties of most rock vary with the different direction. For example, in sedimentary and foliated rocks, the tensile and flexure strength and modulus of elasticity are generally lower in the direction perpendicular to the bending and foliation than the direction parallel to the bending of in some instance, these differences are large enough so that their effects should be considered in evaluating a rock structure problem. However, very little is known about the anisotropic property in the in situ rock. In fact, only major data are available on the anisotropic property in the laboratory site specimens. So that is a very interesting thing for the tensile failure is caused by the stress concentrations at the edge of the thin crack oriented normal to the direction of the least compressive principal stress. For isotropic rocks, conditions for failure will always be fulfilled first for the lowest principal stress. So this is here showing that minus negative come. The value is not negative. It means that the strength in other direction. And also, the most sedimentary rocks have the rather low tensile strength. Typical, only a few megapascals or less. Standard approximation for several applications that then tensile strength is zero. Shear failure, it is occur when the shear stress along some plane is the sample is too large. Is a shear failure. It will be one force is acting this, so the failure is like this. So this is shear failures. And shear failures, this is all given. Failure criteria, there are the most important failure criteria the scientists are given. The Hook and Brown and Drunger pressure, Griffith, and the Morse column criteria. These four criteria are for the rock failure criteria. Morse column criteria. This is a cohesion or inherent shear strength of the material in Pascal atoms and bars. Coefficient of internal friction. Shear stress must overcome the cohesion plus the internal friction in order to produce a macroscopic shear failures. Morse column criteria. So this is a complete Morse column criteria for rock failures. Here is the circle is showing that Morse circle, major principal stress and major stress, minor principal stress. So in this Mohr's circle of stress failure line is showing that one. There is a tan alpha is equal to mu, Mohr's circle, alpha 1 and rho 1 and rho 3. The A is a yes stress, particular y-axis stress, multiplied tan phi, this cot alpha. If the Mohr circle lies below the failure line, the rock does not fail and remain intact. The more than this line, the tangential is a failure. So geometrical solution of stress is in any required direction is provided by Mohr circle. The considering the above stress diagram, the steps are constructed Mohr circle as follows. Construct the set of the orthographical axis and label the vertical axis, that is a failure, and a horizontal axis is the rho. That is a, you can show this is a tau. This tau is the vertical axis is a tau. The horizontal axis is a stress, and horizontal axis showing is the it is necessary the scale of these two axes are equal. Plot the normal stress sigma x and sigma y on a normal stress axis. The shear stress, the tau zy, acting on the right hand edge of the element, directly below the or above the point represent the sigma x on the normal axis. The shear stress is a counterclockwise relative to the center of the element plus sigma tau x z xy below the normal stress axis, and if the shear stress is clockwise related to the center of the element, they plot the tau xy above the normal shear stress axis. So shear stress acting on the selection common with sigma either the above or below the point, but the opposite side of the normal stress axis join the two shear points with straight line. The line will be interrupted normal stress at a point where this point is cut. That is point. So circle with the center normal axis point. Generally, we can sigma y plus sigma 3 by 2 is the center. Basing on center, we draw the circle. It shows that normal things, and introducing the equation of the coordination of the points P into the criteria equation. So of sigma 1 by the principal, major principal strain minor principal strain sine 2b. This is simplified equation. U plus of 2 to sigma 1 plus of or minus cos 2 by. Mu is a tan alpha. Sometimes you're using the, that is a coefficient of friction is concerned, and B is the pi by 4 pi by 2, replace the U and P by 5. So the multiplying by sine side by 2 cos pi by 10. So ultimately they both will be getting this equation. So you can go through the note it down for the further calculation purpose understand. And then phi angle of internal friction, it varies from the 0 to 90 degrees approximately, get 30. The attraction, that is a point where the bar B is the angle, beta is the angle that fulfill the failure criteria. It gives the orientation of the failure plane, varies between the 45 degrees and 90 degrees at point P. The angle 2B give the opposition of the coincidence of the Mohr circle and the failure of the line. So the double that angle. The coordinates are 1 by 2, sigma 1 minus sigma 3 sine 2 beta, and sigma is equal to 1 by 2 sigma 1 plus half of sigma minus 2 cos 2 beta. So overall, 2 beta is equal to 90 degrees plus 5, and beta is equal to pi by 4 plus pi by 2. Then this is another equation for representation of relations in the form of uh, Morse is given the uniaxial compressed strength in pascals. This is the ultimate things that term is square square. Slope, this is a slope, and sigma 1 and sigma 3. A, Y. These are the two cos by flaw 1 minus NB, C 2 B, tan phi 1 plus sin phi by 1 minus sin phi tan phi minus 1 is equal to A plus B square. The Westerline granite triaxial compression, that is a megapascal using Mohr's Coulomb criteria on the saturated rocks. A principle of effective stress is introduced. Subtract fluid pressure for the total stress previously that given the equation, then we ultimately get the following equation. So increasing the pore pressure, the pore fluid can be affect the failure of the rock in two ways. The mechanical effect of the pore pressure, chemical interaction between the rock and the fluid. So increasing pore pressure, it is a typical condition, and the typical condition will get such a way that the Morse Coulomb criteria. Effect of a pore pressure on the failure. Shear stress is unaffected by the pore pressure. Max and minimum and maximum principal stresses are decreased by the same amount. Radius of Mohr circle is unchanged. Center of the circle has shifted to the left. So circle moves towards the failure line when the fluid pressure increases for the material obeying the criteria. That is a very important. So more circles can understand. And then more stress circle. We derive these two equations. This equation represent equation of circle. Sigma 1 plus 2 by 2, sigma minus 2 by cos 2 theta plus tau sin 2 theta. Similarly, sigma minus sigma by sin 2 theta minus tau 2 tan theta. So more stress circle can be, these two are the important equations. Your one upon other. Another more stress circle, sigma 1 minus sigma would give it to the equation, we will equation circle. So it can be drawn as a circle x minus a whole square plus y square equal to r square equation of the this circle. So that is a representation of the y axis and x axis and drawing of the circle, more circle. And more stress circle, a graphical method determine the stresses. The body is subjected to two mutual perpendicular principal stress of unequal magnitude. Body subjected to two mutual perpendicular principal stress of equal magnitude, and unlike one tensile to other compressive body subjected to the uh, perpendicular 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 principal stress plus simple shear stress. And then it's a Mohr stress circle, a body subjected to two mutual perpendicular principal stress of unequal magnitudes. Length AD equal to normal stress on an oblique plane, the sigma n. Length ED, that is given in here, AD, this is from here to here. This is normal stress on the oblique plane. The length ED, that's the ED, this is the vertical, tangential stress on the oblique plane. So length AE equal to, indirectly it can be calculated as square root of sigma 1 square plus sigma n square. So sigma 1 is a major principal stress and minor principal stresses. So these are the differences given. So body subject to mutual perpendicular principal stress, so unequal magnitudes. So this is a representation here. And then theory of failures. The maximum principal stress, one is the Rankine theory is there. Maximum principal strain, already we are saying where variant theory. Maximum shear stress, guest theory. Maximum strain energy theory. Maximum shear strain energy also given here. So maximum principal stress theory, sigma 1, sigma 2, sigma 3 principal stresses in three perpendicular directions. Maximum sigma 1, sigma 2, sigma 3 less than or the maximum principal stress should be less than the maximum stress yield stress that material can bear in tension or compression. So maximum tensile or compression strength of material, maximum principal stress equal to, you can be right. So maximum principal strain theory, sigma 1, sigma 2, sigma 3, principal stress in a three perpendicular direction. Uh, the maximum E1, E2, E3, the given here. That equation is given here. Similarly, this is the maximum shear stress theory. Maximum shear stress is equal to half of the difference of maximum and minimum principal stress is the simple tension and the stress in existing in the one direction only. To uh, prevent failure, maximum shear stress should be less than the shear stress in simple tension and elastic. Maximum shear stress elastic half of the maximum tensile material. So most of the sigma 1, sigma y less than or equal to sigma t, the tensile maximum shear stress should be less than the maximum shear stress simple tension. See here again, simple tension is at elastic limit of the material can be bare. So available stress is equal to simple shear stress by safety factor of safety. So factor of safety can be visualized in such a way that failure things. The factor of safety can be visualized in such a way. The allowing of the difference between the laboratory determination and in situ strength of the rock plus the error introduced by the various assumptions required in the competition of stress and deformation. It is a necessary to use safety factor in the treatment of rock structure problems. The safety factor is defined as a ratio of the maximum stress in the material in service, the working load, to the strength of the material. However, uh, the design specifications for any underground structure for a military or industrial purpose may be vastly different from those for mine. In the former, the structure is designed for the high degree of the safety over a long lifetime, whereas in a mine, because of the economic pressures and a desire to the conserve resource, there is a usual premium and extraction of much ore is possible. The problem may become the one design and opening to that will be remain open long enough to remove the winter safety. In sense of the mine may have the safety factor in the time that. So in practice, factor safety educate structure member is a compression such as a pillar and the side walls. Where a safety factor 4 to 8 is required for the members in tension such as the bedded roofs. Usually the lower values are used in the design of the mines with a relatively short lifetime and a higher value for the opening. long lifetime. These values were obtained from an analysis of a large number of existing structures. In this analysis, the structure stresses were computed assuming a gravity loading, and property of the rock were measured in the laboratory and specified taken from the above structure. Other maximum strain energy theory. So this is also max allowable stress is given. Strain energy per unit volume should be less than that strain energy as per the unit volume in a simple tension at elastic limit that material can be bear. The effects of moisture and pore pressure is also very important factor for the consideration. That is that can be shown in the upcoming things. In general, effect of pore pressure is one of the directional variation, elastic properties of rock affecting the stress rock surrounding underground excavation and the structural member also. So in here we are using sigma 1 whole square plus sigma 2 whole square plus sigma 3 minus 2 Poisson ratio, sigma 1 sigma 2 sigma 1 sigma 3, and sigma 3 will be less than or equal to that is a shear stress, tensile stress over the square. So ultimate max allowable stress can be this equation. And another max the shear strain energy theory, as per the theory is concerned. Shear strain energy per unit volume should be less than the shear strain energy per unit volume in a simple tension at elastic limit. That is sigma 1 minus sigma 2 whole square plus sigma 1 minus sigma 3 whole square plus sigma 2 minus sigma 3 whole square less than or 2 into sigma 1 star whole square. So ultimately the max allowable stress is the same. So then the important the points of above already given. That's a brittle material. Brittle material. The maximum principal stress. Brittle material do not fail in shear. That is a very important fact. It can be noted down. Ductile material. The maximum shear stress or maximum shear strain energy. Ductile material fail in shear because of their yield strength is high. So these two are the important factor for the failure criteria for the brittle material as a ductile. And then coming to the failure theories. So now I going to one of the simple problem is given here for your practicing purpose. The principal stress at a point in an elastic materials are 200 Newton per mm square tensile, 100 mm square tensile, and 50 Newton per mm square compression. If the stress at the elastic limit in a simple tension is a 200 Newton per mm square, determine whether the failure of the material will occur according to the different failure theory. Take Poisson ratio is 0.3. So principal strain theory, maximum strain theory, maximum strain energy theory, maximum, which are the given already above equation we are given the maximum shear strain energy theory, this formula. Keep that values into this one, they calculate that one. Similarly, maximum shear strain, the value put into here and get it to the answer. Similarly, maximum shear strength here. Similarly, maximum principal strain theory here. So these applied by this formula. Uh, So I hope you are understanding the lecture. I would like to briefing again. So there are particularly there is a failure criteria theories are, but it's basically uh, maximum principal stress, a maximum principal strain, and maximum shear strain, and also maximum strain energy, maximum shear strain energy. These are the basic theories of failures. Upon also there is Mohr circle theory, Morse and Coulomb theory is there. Another coming to the uh, Morse criteria and also Coulomb criteria. These theories are helpful to the particularly Morse circle theory. The failure can be Coulomb criteria. The four theories also Griffith theory also by using cracks that will be explained in the coming lectures also. And Hook and Brown also the one has specified failure theories also that the coming class I will explain. But in particular more Coulomb criteria, preparation of a geometrical um, circle, the radius and sigma 1 and sigma 3 differences and tangential that value it calculated the cohesion and also when the circle moving above and below according to the load can be where can be estimations there. So this is the failures of different shear failure, tensile failure, and the tensile failures and in a confined pressure. That means triaxial test. Triaxial pressure, so the value is more in the compression because of the horizontal pressure. So ultimately, you are understanding the basic principles of the elastic property of the Hooke's law. So where the it's unable to bear when the load is released, that will come to the original position, that is elastic nature. So the elastic region specimen return to its original state of the upper stress. The yield point is the permanent change behind this point. Specimen does not return to its original state of the removing of the stress. And also uniaxial compressive strength, uh, the peak stresses, the union compressive strength peak is a ductile region, permanent deformation, but can be still support load. The brittle region, ability to withstand stress, decrease rapidly as the deformation increases. So these three categories, that is elastic, ductile, and brittle, uniaxial compression by elastic Hooke's law can be explained, but same principle we applied every material also. So this is about the overall idea about this failure criteria. Brittle material, maximum principal stress, maximum principal strain, maximum shear strain density can be applied. Ductile material, maximum shear stress and maximum destroyer energy density. So with this, I'm going to concluding the today lecture. Once again, thank you.